Nothing beats. In this video, what we're going to do is we're going to look at a couple of examples of how to use LHospitals Rule, and then we're also going to look at a couple other of indeterminate forms and look at some examples of those as well. Let's go. Okay, let's just refresh our memory. LHospitals Rule says if you got two different functions, say f of x and g of x, which are both differentiable on an open interval I, containing some location x is equal to a with g prime of x non-zero on that same interval I, when at least x is not equal to a. Basically, what do you got? Two functions, f and g, differentiable on an open interval I, meaning they're both continuous as well. And if that happens and you have that both the limit as x goes to a of f of x and the limit as x goes to a of g of x are both 0, or you have that the limit as x goes to a of f of x and the limit as x goes to a of g of x are both either plus or minus infinity, then the rule says right here, limit as x goes to a of the quotient f of x over g of x is the limit as x goes to a of f prime of x over g prime of x. Right, this rule we established in a previous video. However, what we're going to do now is just look at a few more examples so we get a more variety. So let's do some examples. Let's find each of the following limits. Here is one right here. Limit as x goes to 0 of 1 minus the cosine of x over x. Notice, as x goes to 0, what happens? The numerator goes to 0 and the denominator goes to 0, since of course cosine of 0 is 1. And so LHospitals Rule applies. Moreover, 1 minus cosine of x and x are both nice and continuous and differentiable nearby x is 0. So when I apply LHospitals Rule, using the notation that I like to use, put a little h there saying we're applying the rule itself. This is going to be the same as the limit as x goes to 0 of, well, what does the rule say? Differentiate the numerator. When we differentiate the numerator, what do we get? We get sine of x in the numerator, right? Derivative of 1 is 0. Derivative of cosine of x with respect to x is negative sine of x times that negative is sine x. In the denominator, the derivative of x is just a 1. So this is just the same as the limit as x goes to 0 of sine of x, which is 0. An example in using LHospitals Rule. Let's look at a couple more. All right, here is another one. In this case, the limit as x goes to infinity of the natural log of x divided by e to the 2x plus 4. Now notice here, x is not approaching a real number, say a, but rather it's approaching infinity. However, we can approach anything in LHospitals Rule in the x direction, and as long as it has the indeterminate form 0 over 0 or plus or minus infinity over infinity, it applies. So what happens here? Well, as x approaches infinity, natural log of x approaches infinity. As x approaches infinity, e to the 2x plus 4 also approaches infinity. So once again, LHospitals Rule applies. So we apply LHospitals Rule right here like so, using the notation, and get that this limit is the same as the limit as x goes to infinity now. All right, derivative of natural log of x with respect to x is 1 over x. Derivative of e to the 2x plus 4 with respect to x is a 2e to the 2x here. And just cleaning that up, that's the same as the limit as x goes to infinity of 1 divided by 2x e to the 2x. And as x goes to infinity, that denominator goes to infinity. So in this case, the limit is 0 once again. Another example, but in this case, infinity over infinity situation. Let's look at one more before we look at the other indeterminate forms. Here, looks very similar to the first one. Limit as x goes to 0 of 1 minus cosine of x, but now it's being divided by x squared rather than by x. So notice, again, as x goes to 0, the numerator goes to 0, denominator goes to 0. So L'Hopital's rule applies, keeping in mind these functions in the numerator and denominator are nice and differentiable and continuous. So apply L'Hopital's rule. What do we get? This is the same as the limit as x goes to 0 of, all right, derivative of the numerator there is going to be a positive sine of x, and the denominator derivative is 2 times x. Now notice, in this case, once we let x go to 0 again, the numerator goes to 0, and the denominator still goes to 0. So here is an example in which we apply L'Hopital's rule, and the result that we get is another indeterminate form. So as long as at each step the conditions of L'Hopital's rule applies, we can keep using it. And in this case, sine of x over 2x definitely goes to another indeterminate form, 0 over 0. Sine of x and 2x are both nice and differentiable. And so we can go ahead and apply L'Hopital's rule again, giving us limit as x goes to 0 here. Derivative of sine of x is cosine of x. Derivative of 2x is just a 2. And as x goes to 0, this limit goes to 1/2. So it can be done in that you may have to use L'Hopital's rule multiple times within a limit. And hopefully it exhausts itself. If it doesn't, then you may have to use some type of maybe more algebraic methods throughout it. So now that we've seen 3 different examples here of just using L'Hopital's rule, some of these limits become a little more obscure. And so let's take a look at some of these other situations, and what they encounter here is, well, we're going to look at what is called indeterminate products and indeterminate differences. One way or another, what we're going to see is L'Hopital's rule comes into play. So how do we define these? First of all, an indeterminate product. In this situation, we have a limit like so. The limit as x goes to a of a product of 2 functions, f of x times g of x, but in specific, the limit of one of the functions, say f of x as x goes to a, is 0, while the limit of the other function, g of x as x goes to a, is either infinity or negative infinity. So you get this form 0 times infinity or 0 times negative infinity, and in that case is what we call an indeterminate product. You think of one of the functions is getting arbitrarily close, tiny to 0, while the other function is growing without bound either towards infinity or negative infinity. So totally tiny number times infinitely large gigantic number, when you multiply them together, what does that actually become? An indeterminate product. And we'll see an example of how to approach such a situation. The other type, as we mentioned a moment ago, is what is called an indeterminate difference. And in this situation, we have a limit, well, as x goes to a of a difference of 2 functions, say f of x minus g of x, where both of the limits as x goes to a of f of x and g of x approach infinity. So you have the situation infinity minus infinity, and again, that's not necessarily going to be equal to 0. It could be anything, hence indeterminate. So how to approach such a situation like that? Let's see. Now notice again, both of these situations that we just looked at, the indeterminate product and the indeterminate difference, we don't have indeterminate forms that are either of the form 0 over 0 or plus or minus infinity over plus or minus infinity. And so we can't necessarily use L'Hopital's rule directly, because L'Hopital's rule says that the limit has to have one of those 2 indeterminate forms. Rather, what's going to end up being needed is that we're somehow going to have to manipulate the limit one way or another so that it becomes an indeterminate form. And then from there, once we get it in indeterminate form, we can go ahead and then apply L'Hopital's rule from there. So let's look at how this can happen. Let's find a couple of more limits here. In the first one, here was a limit as x goes to 0 from the right of the product x times the natural log of x. So notice, in this case, as x goes to 0 from the right, that goes to 0. And as x goes to 0 from the right, the natural log of x goes to negative infinity. And hence, this is an example of an indeterminate product here. And so what will we do? Well, we can't use LHospitals rule right now because it's not of the form 0 over 0 or plus or minus infinity over infinity. And so somehow we have to manipulate the limit so that it becomes one of the two forms. And in this case, when we have an indeterminate product, the strategy is really take one of the functions in our product, either f of x or g of x, in this case x or the natural log of x, and divide by the reciprocal of that function. Let's try that. Let's rewrite this as the limit as x goes to 0 from the right. And what I'm going to do is I'm going to divide by the reciprocal of x here, giving me the same limit, but in a different form, the natural log of x divided by 1 over x. So that's literally the exact same thing, right? Because dividing by 1 over x is just the same as multiplying by x. However, it's in this other form now. How is this helpful? Well, notice as x goes to 0 from the right, natural log of x still goes to negative infinity, but now 1 over x goes to infinity. So by dividing by the reciprocal of x here and taking the same limit, we now have an indeterminate form in which we can apply LHospitals rule. And that's really a general strategy when dealing with indeterminate products. From here, we can actually go ahead and apply LHospitals rule and get that this is the same as the limit as x goes to 0 from the right of derivative of the natural log of x is 1 divided by x divided by derivative of 1 over x is the same as the derivative of x to the negative 1, which is a negative 1 divided by x squared. So did this help? Well, let's clean this up once again. This is the same as the limit as x goes to 0 from the right of, well, that's just a negative x if you simplify that. 1 over x times a negative x squared over 1. Simplifying gives a negative x. And now as I take the limit as x goes to 0 from the right of negative x, this is 0. So, an example of an indeterminate product. How about another example? Let's take a look at this one. Here is the limit as x goes to 1 from the right of the difference of the two functions, 1 divided by the natural log of x minus 1 over x minus 1. So we know that natural log of 1 is 0, and for values of x larger than 1, the natural log of x is positive. And so as x goes to 1 from the right of 1 over the natural log of x, that's going to go to positive infinity since the denominator is blowing up, the entire thing is blowing up because the denominator is approaching 0 from the positive direction. Moreover, 1 over x minus 1 also goes to infinity since as we approach 1 from the right, x minus 1 approaches 0 from the positive direction, and hence we get an example here in which we have an infinity minus infinity situation, and that is our situation in which we have an indeterminate difference, as we say. So how to deal with this? Well, it seems reasonable that we could find a common denominator here and try to rewrite the limit in a different form so that we have a quotient, and hopefully we'll have some type of indeterminate form for which we can apply LHospitals rule. So oftentimes when we have indeterminate difference, the strategy is, at least first of all, go ahead and attempt to find a common denominator and then rewrite the function we're taking the limit of. So let's do that. Limit as x goes to 1 from the right of, well, the common denominator here is just the ln of x times x minus 1. So we get an x minus 1 from the first term minus an ln of x from the second term, all divided by x minus 1 times the natural log of x. So there's a lot going on there, but let's see what happens. Well, notice in the numerator here, as x goes to 1 from the right, we get a 1 minus a 1 minus a 0. So the numerator goes to 0. And in the denominator, we have a 1 minus 1 is 0 times ln of 1, which is also 0. So by finding that common denominator, it put this indeterminate difference into an indeterminate form for which we could then apply L'Hopital's rule. And so let's go ahead and apply L'Hopital's rule and see what we get. All right, applying the L'Hopital's rule, we get the limit as x goes to 1 from the right of, all right, derivative of the numerator. Derivative of x is 1, derivative of negative 1 is 0, and then minus the derivative of ln of x, 1 over x. All divided by, notice in the denominator, by differentiating x minus 1 times the ln of x, we actually have to apply the product rule. We can treat x minus 1 as the first function and the ln of x as the second function. So the derivative of x minus 1 is just a 1 times the ln of x leaves me with ln of x. And then plus the derivative of ln of x is 1 over x times an x minus 1. So x minus 1 times a 1 over x. Let's just make that a little bit more clean there. Now I'm just going to rewrite it a little bit more by multiplying the x minus 1 times the 1 over x to get the limit as x goes to 1 from the right of a 1 minus a 1 over x, all divided by ln of x, and then plus, notice x times 1 over x is just a 1, so plus a 1, and then minus a 1 times 1 over x, so minus a 1 over x. So what's going on there? As x goes to 1 from the right, notice the numerator again goes to 0, 1 minus 1 over 1. In the denominator, ln of x is going to go to 0 because x is going to 1 from the right, plus a 1 minus a 1. So again, we get a 0 over 0, another indeterminate form. And so another example in which we have to apply L'Hopital's rule more than once, for which we definitely can do here. Let's do that. Applying L'Hopital's rule once again, we get the limit as x goes to 1 from the right of, all right, again, we're focusing on this function right there. Inside the limit, derivative of the numerator is going to give me a positive 1 over x squared in the numerator. In the denominator, derivative of the natural log of x is a 1 over x. Derivative of 1 is 0, and then plus a 1 over x squared. So now we can see as x goes to 1 from the right, we actually can evaluate this limit. The numerator is going to go to 1, 1 over 1 squared, and the denominator is going to go to 1 over 1, which is 1, plus another 1 over 1, another 1. So 1 divided by 1 plus 1, which gives us the result of a 1/2. So as we can see, some of these limits can get involved in which we have to not only apply algebraic manipulations to put it into an indeterminate form, but also we may have to use L'Hopital's rule more than once. And now we've seen several examples in this video. The first 3 were just L'Hopital's rule straight up. And then the second 2, an example of an indeterminate product and the strategies that went along with that, and also an example of an indeterminate difference and the strategies that went along with that. And so that is it for this video. It's going to be one more video on L'Hopital's rule, which has to do with the special case of indeterminate powers, how to deal with those, and what those are even made of. Until that next indeterminate powers video, it is math and beats later.